Hello everyone, welcome to the webinar of today. I see participants, the number of participants is still growing. Perhaps we can wait 1 more minute. We still have plenty of time. Usually we start with a brief introduction of CMCC itself. So perhaps we can start with that. And after this very few slides, I will present the speaker and we can start shortly. So next slide, please. So the mission of CMCC, if you let me read through, is to investigate and model our climate system and its interactions with society to provide reliable, rigorous, and timely scientific results to stimulate sustainable growth, protect the environment, and develop science-driven adaptation and mitigation policies in a changing climate, and to develop foresights and quantitative analysis of our future planet and society. Next slide, please. As you see in this map, CMCC has branches, has offices in different places across Italy. Next slide, please. CMCC is also directly linked to a number of academic and research institutions in Italy. Just to mention a couple, you see the Polytechnic University of Milano, University of Bologna, University of Venice, and all the other academic and research institutions listed on the left. Next slide, please. CMCC is also produces interdisciplinary research. So here you can see all the different divisions indicated by the initials in bold. I mean, we don't need to go through each of the divisions. I will only mention that this webinar is hosted, is organized by the Climate Simulations and Predictions Division in Bologna. Next slide, please. We should mention that CMCC operates its own supercomputing center since 2008, and this is located in southern Italy, in Lecce. And currently, CMCC is building a new supercomputing center, which includes upgrading the computing and storage facilities. And you can see the technical specifications on the right-hand side. Next slide, please. It's important to mention as well that apart from publishing research articles, publications, CMCC is engaged also in education. There are PhD programs in the different, linked to the different institutions that I mentioned earlier, that you showed earlier. And there is also communication activities and organization of events, as for example, this webinar. And next slide, please. It is useful information that this webinar is recorded, and automatically your audio and video will be deactivated by default. But if you need to raise a point or make a question, you can use the question and answer section at the bottom, or use the raise hand feature. And at the end of the talk, we will accept questions. Next slide, please. As I mentioned, this webinar will be recorded, so if any colleagues of yours couldn't attend, or if you would like to come back and see this again, the link will be shared, and feel free to write to webinar@cmcc.it, that the email that you see at the bottom left, and also, of course, follow us on social media, Twitter, Facebook, Instagram, etc. So next slide, please.
So that's the last one.
Yes, of course, this is the last one, and we can move to the presentation. So meanwhile, I will introduce our speaker for today. Do we see the slides? Yes. Okay, thank you. So Iuliia, Dr. Iuliia Polkova is a research scientist based at the Institute of Oceanography of University of Hamburg, and Iuliia has a background in engineering that she obtained from the Kiev National Aviation University. After obtaining her master's degree in 2008, she worked as a junior researcher on environmental safety in Ukraine. And in 2010, she joined the Max Planck Institute for Meteorology, where her career on climate predictability began, and where she worked on her PhD project investigating oceans' contribution to climate predictability. Then in 2014, as a postdoc, Iuliia joined the Institute of Oceanography and worked on large German, national, and European projects to advance understanding of the predictability of the climate system. She contributed to the development of the Decadal climate prediction model for the German Meteorological Service, DWD. And her research interests encompass designing decadal climate prediction systems, including data assimilation, initialization, and ensemble generation, and identifying mechanisms for predictability and early warning signals. So Iuliia has also specific interests in linking climate predictions to specific applications. Finally, in 2020, she received a research grant from the German Research Foundation to identify further potential for improving climate prediction systems via coupled data assimilation. And today, she will present from her work towards model consistent initialization of decadal climate predictions. So, Iuliia, the floor is yours. And
yeah, thank you, Panos. Thanks for the nice introductions. Indeed, I would like to talk today a little bit about how decadal climate predictions are made and exactly how decadal climate predictions are started. So decadal climate predictions are forecasts of important climatic indices for several years ahead. They are possible due to slowly varying processes that are happening in the Earth climate system and due to response of the climate system to the external forcing, such as greenhouse gas concentrations, aerosols, solar radiation. Several research centers around the world produce this type of information operationally, and these decadal climate predictions are provided and gathered under the umbrella of the World Meteorological Organization, and this project is led by the Met Office. So what is exactly initialization for those who are not in the topic? So this is basically how we start climate predictions. We need a certain starting point, and this is the recently observed climate state. So these are all available observations that we have about the ocean, about the atmosphere, sea ice, or land. And obviously, these are very many observations, and initialization and data assimilation takes care of how they are all introduced into the climate prediction system. which of these observations matter for the quality of predictions. And there are, what one can say here, that there are many ways how we can introduce observations, and there can be also different outcomes from this procedure. And I would like to show you a couple of examples of how initialization matters for the quality of decadal predictions. So there have been very many publications on how exactly to initialize decadal climate predictions, and not all of those publications are even listed here. The first three are very famous, from Smith et al., Kindleside, and Polman. Those were the first publications on initialization of decadal climate predictions. They are the most cited. So it matters for the quality of climate predictions how we introduce observations into the model. If we do this wrong by any chance, we of course try to do this right, but in case something goes wrong during the data assimilation or initialization, the skill in predictions can quickly be lost. And that's why there is a substantial research to understand how to do this right, so that the prediction skill in decadal climate predictions remain as long as possible. So in the title of my talk, I had this words towards model consistent initialization. So what that means for me, this means the initialization that is respecting model's dynamics. I would like to show a couple of examples where this was the case or not, and how it led to certain outcomes in the predictions. So one of the examples is the spurious El Niño events that can be generated during initialization. Of course, ENSO itself is not the target of decadal climate predictions. We are more interested in variability that happens on interannual and multi-annual time scale. However, we do initialize also, and we do have ENSO in the first years of predictions. So for ENSO prediction, it's very important that the subsurface of the ocean is in a balance with the atmospheric forcings in the form of the wind stress. So the very first initialization methods that we have inherited from the seasonal prediction community were using nudging of the atmosphere and nudging of the ocean towards already existent ocean and atmospheric reanalysis. So when we introduce this external reanalysis into the components of our climate model, hopefully that they reflect that balance of the subsurface of the ocean and the forcing from the atmosphere. If not, then the model tries to achieve that balance in the prediction mode, so it triggers El Niño events and try to achieve that balance in the between the atmosphere and the ocean. So these are examples that have been reported in several decadal prediction studies. The one is from my study and one from Iuliia et al. 2017. So that balance between ocean and atmosphere can be evaluated by the difference between the pressure gradient force, which represents the subsurface of the ocean, and the zonal wind stress. So that difference should be very close to zero. For instance, in the historical simulations which do not use any information about ocean or atmosphere observation, that is used in our study as a reference. And we have compared several initialization methods, and we see that that difference is larger than in the reference, suggesting that some of the initialization methods have a greater potential to have this spurious El Niño events than the others. And in the paper by Liu, who also analyzed several initialization methods, such as coupled for Dubar, the full field nudging, the anomaly nudging, they show, for instance, that the full field nudging was the most prone to have the spurious El Niño events, as you can see from this black hooks in the middle panel. Anomaly nudging was a little bit less prone to have this artificial El Niño events. as we know the answer, we cannot really predict very far into the future. This is also not the aim of, although this would be great, of course, if it worked, but so far it does not in decadal climate prediction. So here you can see the scale for the surface air temperature for the years 2 to 5 of the climate predictions. And this is a prediction scale which is evaluated by the correlation between the predictions and the verification data set. And everywhere where it's red and dotted, it's significantly correlated, and where it's negative or close to 0, then it's a bad prediction scale. So we see that in this Eastern Pacific, the decadal predictions keep having poor scale. This is an example from the MICLIP project, where we had one prediction system which went through different development cycles. We have tested a great deal of different initialization and ensemble generation methods. And in this particular example, it shows that the method that directly assimilated observations into the ocean, it's this one. And the method that aimed to filter out some high frequency variability, they did a little bit better in the equatorial Pacific. But overall, this imbalance between ocean and atmosphere initialization might go beyond this first year of predictions. So another example is also from the MICLIP project, where I worked, as Panos introduced. In one of the experiments, we had a very poor performance of decadal predictions in the Atlantic region. So there were very large errors in the sea surface temperature. And Jürgen Kröger, he was evaluating what was the reason for that, the bad performance of one of the initialization experiments. So he looked into the ocean circulation. For instance, here we can see the ocean heat content from the experiment which was performed really bad. That was a full field initialization, and another reference experiment which was based on anomaly nudging. So when we look at the ocean heat content in the nudging, in the assimilation runs, which is the source of initial conditions for decadal climate predictions. So in red is the reference data set, a NOAA product. In the bluish colors is the AURA S4 analysis, which has been nudged into the model. And in black colors is the nudging run itself. So when we just look at this nudging run and ocean heat content, we see that it seems that the nudging run is perfect. No problems can be detected in the nudging run. Well, when we look at the predictions themselves, these are predictions for the years 2 to 5, then we see that there is a discrepancy from the assimilation run, and in the full field we see that predictions have nothing to do with the source of initial conditions or the original reanalysis that was assimilated into the model. But Jürgen kept looking further, and he decomposed the ocean heat content into their surface heat flux in the red curves, and the heat transport in the green curve. The sum of these two is shown in the blue curve, and the black curve shows the ocean heat content tendencies. So he analyzed the heat budget in the nudging runs and in the first year of the prediction. And in this run, which showed very large errors in the sea surface temperature, he noticed that there is a gap between the blue and the black curve, which suggests that, so basically there is a discrepancy between the ocean heat content tendencies and all heat fluxes, which suggests that the ocean heat budget is not closed in the nudging run. He further analyzed that in all experiments, and he noticed, for instance, that the heat budget closes in the first prediction year. So the model tries to clean up the mess that has been done during the nudging run and reach the balance in the region. what is interesting in here is that the ocean heat content has a different variability than the assimilation run, which it shouldn't, because the ocean has a very slow variability, and we expect there is a certain persistence from year to year. But we see that this variability of the ocean heat content is dominated by the variability in the green curve, which is the heat transport. And that green curve in the prediction looks a bit similar to the green curve in the nudging, which suggests that the heat transport from nudging persists in the prediction, and the error has been associated with the heat transport problems. So there are several problems with the nudging assimilation, which can result from ocean heat content being directly affected by the changes due to sources and sinks of heat, which are introduced by nudging in the nudging terms. The nudging itself changes density structures along the lateral boundaries of the ocean, introducing or changing the geostrophic balance and introducing certain in and out flows in the interior of the ocean. It can also change the temperature at the surface and modify the heat flux exchange between ocean and atmosphere. So ocean heat budget can be one of the diagnostic to figure out what's going wrong in assimilation runs. Another diagnostic, which has been introduced a while ago, but I just learned about this recently, is analyzing if density is dominated by the temperature or by salinity, because in the Sapologia, it turns out that in different models, this mechanism is different, and it can also change from their assimilation run to prediction. So density mechanism could be also another diagnostic to figure out what's going on with the nudging and prediction runs. So another part, important part about initialization of climate predictions is that, of course, it's not very surprising, but we know that variability of different models can be slightly different, and variability also of the reanalysis that we introduce in our models can be also different. So here is an example of the variability for the temperature for the 6-meter depths, 300-meter depths, from 3 to 700-meter depths. So the upper panels show temperature variability and the lower salinity variability. So we see, for instance, that in the MPISM model, there is more going on in terms of variability than in the ORIS-4 analysis. So we have to keep in mind that we try to initialize, for instance, the model which has this variability with the ORIS-4 analysis which has this variability. So it might pose another problems. So there were two methods that have been developed and which try to shape or fit the observed variability to model variability, so that the model does not complain too much when switching from assimilation to initialization mode. One of the methods implies projecting external reanalysis onto the modes of variability from the climate model. So here, of course, the question is how to derive those modes of variability. In this method, I use the global AOF modes. And another method suggests scaling external reanalysis by model variability. So, for instance, there where we have where the model has high variability, we would scale that by the model variability. But there where the model shows no variability, then that signal would be damped from the external reanalysis. But I think that so both the studies have reported certain improvements in certain regions, but I think both of them, they're slightly failed in the North Atlantic region, which is very important for their decadal predictions, as it's supposed to be dominated by internal variability or in addition to the external forcing response. So for instance, in the first method, it failed in a way that the modes of variability from the model turned out to be very different from the modes of variability from the reanalysis. So in the projection step, a lot of variability from the observations were filtered out. And so we can see that the skill seems to be good here, but when we look at this, it's mostly the skill comes from the external forcing. While in the second method, we see that there is obviously a negative skill along the Gulf Stream front. And I think here the problem of this method is the problem which is very common to all very many initialization methods is related to the model biases, such as very zonal Gulf Stream. You know that in many models, especially large resolution, the Gulf Stream is a little bit too straight from one boundary to another, while in the observations and maybe even in the ocean reanalysis, it's more steep. So assume that north of the Gulf Stream, we have negative anomalies, and south of the Gulf Stream, we have positive temperature anomalies. And when we try to introduce this into the model, we receive something as in this middle panel. So we try, what happens is that we get a certain negative anomaly then appears to be south of the Gulf Stream, and some positive anomaly appears to be north of the Gulf Stream. And so I think that even the second method, which is designed to kind of reshape or observed variability, still would have this problem that we would initialize some artificial dipole, which is completely artificial here. So another example is the Atlantic meridional overturn circulation variability. So this is again an example from the MICLIP project where we had one model and have tested different initialization methods. So this is the overturn circulation for the latitude 26 north for the lead year 1 and prediction year 5. So you don't have to distinguish all these different curves. So just this red dashed one, this is the ORS4 analysis. And the other initialization, they have it in different ways as a source of initial conditions. So what you can see in these curves moving from year 1 to year 5 is that in the year 5, the ocean circulation has been damped. So you can see here there is a very large signal for the ORS4 analysis. It can be up to 6 Vedrov variability. But you see that for model, it seems to be very large, and all the curves look a bit flatter in the lead year 5 than in the lead year 1. So the model damped this very strong variability to the level of model variability. On the previous slide, it was certain issues with the variability. This slide is about the mean of the overturn circulation. Previous studies have reported that, so the studies by Smith, but also Kröger, that in the full field initialization, the overturning cell might be disrupted or have some discontinuities because in the Atlantic, the region is highly variable. There is a lot of going on along the Gulf Stream front, but also near the Florida Strait. So if we don't map observed anomalies or observations in general into the model, this may cause the disruption of the cell or introducing some cells in between in this full field initialization. So this is a result from my current work where I compare the coupled nudging experiments, the anomaly one, the full field, and the coupled for Devar. So we see that in the full field, in different realization of their assimilation, we have this disruption of the amok cell. The alternative would be just to use anomalies of observation and add them to the model climatology, so that we don't impose any shocks and drifts. But here the problem is that for this particular model, the overturn circulation is very weak. while it has to be more or less like in this ocean reanalysis. So the question is, what would be less harmful for climate predictions to start from the AMOC, which is might have more realistic strengths, but has a split in AMOC, or would it be better to start from the complete cell, but from the weaker overchain circulation? I'm interested also to analyze how is that in the current CMCC decadal predictions. What is exactly the effect of dynamically consistent or inconsistent initialization of the ocean circulation on the ocean surface and the atmosphere? And I'm currently staying as the visiting scientist at the Met office, and I hope that maybe we can gain some insight in this during my stay here. So why do we think that the climate predictions can be improved? So climate predictability comes from internal variability, things that happen in the climate system without external forcing. So for instance, ocean is moving water from here to there, distributing heat properties, the salt properties, and external forcing, so response of the climate system to greenhouse gases, aerosol forcing, etc. So climate predictability can come from both. And if we improve the internal variability, improve the biases, then maybe we can have an enhanced skill due to internal variability. The other reason is that we are trying to evaluate our top margin up till where we can expect improve climate predictions. And for this, we often use potential predictability studies, which are based on the model world. And they are used to suggest us that there is way more potential predictability than in the current predictions that we actually have, that we assess against the observations. So one of those studies is a bit later paper by Bohr from 2013, who shows, for instance, here the potential prediction skill for the globally average surface temperature. So here you can see this potential prediction skill and the actual that we have now. So there is a gap, and this gap can be associated with the internal variability component. And we can, if we can close this gap here, then we can improve climate prediction theoretically. So one of the problems with this concept of potential predictability studies is that if Earth system models underestimate or underrepresent real-world variability, then this potential predictability might be too optimistic. Another kind of aspect here is that given the signal-to-noise paradox, this assessment can also turn out to be pessimistic, as the signal-to-noise paradox suggests that the models can predict observations way better than they can predict themselves. So the truth is that we don't really know the limit of predictability, and we don't know up till when advancement of initialization of data assimilation method can improve the prediction skill. But in case we still trust in the potential predictability studies and would assess potential skill, for instance, for the sea surface temperature for those years 2 to 5 that I often showed in the presentation, and subtract the actual skill from potential skill, then this would be the regions where we could expect improvement in the Atlantic Ocean, in the Eastern Pacific, in the Southern Ocean. So one of the aspects that we can see also on different conferences related to decadal climate predictions is that we often use compare them against the historical observations, the so-called uninitialized predictions, which do not use any information about the observed state of the ocean or the atmosphere. And here is the prediction skill from decadal predictions minus is shown the skill from decadal predictions minus the skill from historical simulation for the first year of prediction, year 1 to 5 and 6 to 10 from the paper of Bilbao 2021. And so wherever it's red, it shows that there is added value from using observations, and for the years 1 to 5 and 6 to 10, not so much, which is a little bit depressing result for those who are working on initialization and data assimilation. But when we look a little bit more into their what's exactly going on behind those prediction skill assessments, then we can see that, for instance, historical simulations cannot beat decadal predictions on the short time scale, such as 1 year, for instance, in the Linus 3.4 region, because sea surface temperature is shown. In red is the observation, in blue is the prediction, whereas historical simulations are shown here in black, and the ensemble spread in the gray shade. So it's not surprising that these two curves are not correlated, because historical simulations are not synchronized with internal variability. Also, when we look further into the later lead times, such as years 2 to 5, here is the North Atlantic subpolar gyre surface air temperature, again in bluish for predictions and in gray for the historical simulations. And when we look at this statistics here, for instance, root mean square error shows 0.21. For the historical simulations, it's 0.20. It's almost the same. At the anomaly correlation coefficient shows 0.90. For the historical simulations, it's 0.71. Both of them are significantly correlated. If we would do any skill scores, the probably would show that initialization does not do much. But for me, predictions shows better results than the historical simulation here, because it predicts this multi-year variability in different periods. So I think that probably for certain users, they really, as somebody said, they don't care whether prediction skill comes from internal variability or from the external forcing. The main thing that there is a good prediction skill and that information. So I think that historical simulations can be used in certain climate services which are interested in trends and long-term variability, probably. But I think when we're interested in the regional and maybe really this year-to-year variability, then I think that decadal predictions can be more precise there. So in the remaining presentation, I would like to show all possible initialization methods that have been used so far, and a bit sort them out to find certain structure there. So the very first initialization method that we have inherited from the seasonal prediction communities were anomaly and full field initialization. In the full field, we start prediction close to the nature climate. As time progresses, the prediction drifts toward the model mean state. So to avoid that, we can start climate predictions close to the model mean state. This is so-called anomaly initialization. So different studies have been carried out to figure out what's better to have, to allow the bias in the anomaly initialization, or to kind of have the drift, which can be diagnosed and removed from predictions. So what is less harmful from that? And so my understanding, there is no real consensus. When we look at the semi-5 decadal predictions, then it was that half of the groups used full field and approximately half used the anomaly initialization. So that seems to be a model-dependent choice. Then we can have a strongly coupled data assimilation or weakly coupled data assimilation. In the weakly coupled, initialization methods are applied to each individual component of the climate model, and each component receives information about the observations in other domains indirectly through flux interactions at the model boundaries during the forecast mode. So there is an idea that a strongly coupled data assimilation might lead to better results because they simultaneously exchange information between model components during assimilation, and so that ocean is more updated about what happens in the atmosphere, and atmosphere is more updated about what happens in the ocean. However, strongly coupled data assimilation are a bit complicated and more advanced to realize, and there are, to my knowledge, few strongly coupled data assimilation that are used in decadal prediction so far. Then we can have a native data assimilation products to initialize predictions on non-native data assimilation products. So non-native data assimilation products means that we would use, for instance, external atmospheric or ocean reanalysis and try to put that in the climate prediction system. And those external reanalysis were produced with the different models than components of the prediction system. That's why they are called non-native. Native would be if you directly assimilate temperature, for instance, salinity profiles into the ocean and directly assimilate atmospheric observations. So here the risk is that if we introduce these external products into the model, then we might introduce errors from another model into our prediction system. Or as I showed with the example, that variability in that product can be really different than variability in our model, which can also cause problems. Then we can have coupled data assimilation products or uncoupled data assimilation products. So coupled data assimilation product would mean that we would have Earth system reanalysis, so a completely coupled ocean atmosphere reanalysis, and there are reanalysis like this, but they are rather pilots. They're really few so far. But their idea is that maybe coupled reanalysis could avoid any miscommunication of information between model components, such as I showed you for the example of the ENSO. So when we list all these possible kind of setups of how we can introduce these observations, then nudging would probably fit to the non-native uncoupled data. Using non-native uncoupled data assimilation product, it would be weakly coupled data assimilation, and we could test either anomaly or full field here. In the ensemble Kalman filter, which is the second most used data assimilation for decadal climate predictions, there are more variants. You can make it native coupled. You can still have it with non-native uncoupled data assimilation products, as some research centers, for instance, still nudge the atmosphere toward external reanalysis. You can make it strong. You can have it weak. There is more playroom here. It can be also anomaly or full field. I don't know exactly what is the setting in the CMCC experiments, but in the CMCC decadal prediction experiments, the situation was that most of the assimilation runs were non-native uncoupled, weakly coupled, and anomaly or full field. So when we look at these different studies from different research groups, and one can have a feeling that the prediction skill has leveled out. So people try different initialization methods, but they really don't lead to very striking improvements. And I argue here, maybe we just do some kind of minor tweaking on initialization, and maybe because of that, we have minor effects so far. So nudging and ensemble Kalman filter are the most tested assimilation and initialization methods for decadal predictions. And when we look at this list, so the question is, would this mean that native coupled and strongly coupled and anomaly initialization would be the method which is the most shock caretaking, or would it bring us more kind of unexpected problems to solve? I'm interested also to understand the windows of opportunity for decadal climate predictions in terms of initialization, what we can learn, for instance, from simplified models, for instance, from the Lorenz model, which is significantly tested in many climate applications. For instance, we can learn at least two things from the data assimilation in the Lorenz model, that not all variables are equally important for the quality of their analysis. the temporal data coverage and the simulation window matter for the quality of data assimilation product. So the first one, so there are 3 variables in the Lorenz model. We can assimilate only observation for one variable X, for just for variable Y, or just for variable Z, or for all of the variables. When we assimilate observations for all the variables, then the errors in the reanalysis, which is this purple curve, are very small. So the errors are close to 0. When we only initialize X variable, then the errors are quite low as well. When we initialize Y, the errors are also quite low. But when we initialize Z, the errors are quite large. So in these 2 cases, the errors are low because X and Y are cross-correlated, and initializing X also introduces kind of information about the Y variable into the model, while the Z variable is not cross-correlated with X and Y to that extent. So then we can have more data for assimilation, then the errors would be small, and we can have less data, then the errors will be large. So of course it's better to have more data than less for the assimilation. So what this and other simplified models can teach us in how to do data assimilation for decadal climate predictions. So which variables are sufficient to constrain? So far, we initialize temperature and salinity in the ocean, and this would initialize the density, and we expect this would initialize currents. And the question which is bothering me is when we have so many different realization of AMOC, why do we have this leveled out scale for sea surface temperature? Why the sea surface temperature is more similar than all these different AMOC realizations? So we also try to, for the coupled processes, we try to assimilate or initialize coupled ARC fluxes. And I know research groups which exactly for this reason, in order to have these coupled processes, they would assimilate ARC fluxes, and the others, they would not. They would let the model do the trick, not to destroy this ARC interaction. About the variables with high and low cross covariance, I don't have a very good example, but I think there is more and more evidence that, for instance, sea surface temperature initialization would not be sufficient. So whenever we initialize temperature, there is also important to initialize salinity, because in certain regions that they contribute in a compensating way to the density. Which special coverage would be sufficient for initialization? Do we need to initialize globally in certain regions? So the paper by Karasi suggests that, for instance, we cannot exclude the poles. The poles are polar regions are very important for the prediction scale at decadal time scale. There were also studies which initialized, is this sufficient just to initialize the surface, the upper ocean? We don't have observations of ocean below 2,000 meters anyway, but do we need to initialize that? So again, the studies suggest that the deep ocean would be necessary to initialize if we're interested in the prediction of the ocean circulation, but if we're interested in the surface variables, then at least upper ocean should be initialized. There have been methods tried to carefully map variability in sensitive regions, but I think we need more iterations of those methods. Which temporal data coverage is sufficient? There is a concern from certain research groups that the reconstruction of the past climate before the Argo era, if we can trust those prediction skills before that period or not. Also filtering out high frequency variability. Maybe we can, if we have a method to filter out something that the model cannot predict anyway, that would improve prediction skill at decadal time scale. So here I come to my last slide. It may seem that the skill of decadal climate predictions is saturated, and it seems not to improve much, although we try different initialization methods. And I argue here because maybe we we have more things to try here. We have seen the rapid drop of skill unless we did something really wrong during assimilation, like in that experiment that I showed you with the ocean heat content, heat budget. So there is a lot of technical implementation that can be tested. And I think we can maybe take advantage of this large SEMIP experiments and also try to analyze in more detail assimilation runs, because usually assimilation runs, they are more like intermediate step, and I think they don't receive very much attention there. I am interested to explore more windows of opportunity from the simplified models, and I think we can also try to improve the model's response to external forcing, because it's also a very important source of prediction scale at decadal time scale. So thank you very much for your attention. I'm happy to take questions.
Thank you very much, Iuliia. This was a very nice mapping of all the issues faced in initializing climate predictions. We do have some questions already raised. So we have, let's say, 10 minutes time, and we can take some questions right away. So do you all hear me, Iuliia?
Yeah.
Okay, just double checking. So there is a question from Laura Zamboni, and maybe we can start from that. I read through from the question and answers. Why is the goal to produce multi-year predictions rather than next year? There seems to be a gap between seasonal forecasting and decadal. Then, and what is next? And next year will be massively useful in industry. So this points to the, it's a question for you related to some of the things that you presented earlier on in your talk.
Yeah, I think that maybe there is a gap in my presentation, but the decadal predictions, they do predictions for the first year, but also then for the later, for up to 10 years actually. So they provide predictions for the first year, but we want to figure out where is this margin until when these predictions are really good. So the climate predictions that exist, there are subseasonal predictions which are covering several weeks up to a month, then seasonal predictions which are covering from 6 months up to a year. Decadal predictions, they cover the period from 1 year up to 10 years ahead. So there is all this different type of information, and in decadal predictions, we are interested to find the margin until when climate is predictable, and to have this information as much as possible. But annual predictions are also exist.
Right. In fact, in some of your slides, there was there seems to be hope also to improve predictability in this interannual time scale. And there are initiatives to produce also extended seasonal forecasts that will, let's say, bridge the gap. A second between seasonal and decadal. There is another question also from Laura that we can read. Laura is asking which variables are skillful at the present, whether for which variables do we have skill, and whether there is potential to exploit for other variables. For example, what is the current and potential skill of mean and extreme quantities? So here is a question regarding predictability of extremes.
Yeah.
I don't know whether you would like to comment on this.
Yeah, I'll try. So there is currently we see, I showed you the maps of the surface air temperature, sea surface temperature, which shows the prediction skill in the figures that I showed for years 2 to 5, but it can be extended also up to year 10. So there is prediction skill. So in those maps, the skill is usually not separated in internal variability and external forcing. So there is skill in temperature, and it mostly on the longer time scales comes from the external forcing, but in the first years, it comes from the internal variability in certain regions. So the temperature-based, I think, characteristics can be explored more, maybe even in the extreme quantities as well. So anything that is temperature-based, extremes that are temperature-based can be explored more.
Indeed, yes. And there is research going on in this direction. There are some more interesting questions. I will try to use the most of the time we have left. There is a question from Stefano Tibaldi. I read. Is there anything which can be learned from non-linear normal modes initialization technique, much used in the 80s in numerical weather prediction operational world? Will it be possible to compute linear first and then maybe even non-linear normal modes of a global numerical coupled climate model? This is the first question.
Yeah, I'm not really sure. Maybe we can discuss this.
Yeah.
Separate. Yeah, but that's an interesting question. I don't know exactly.
In fact, you don't really. You discussed this.
Yeah, how to extract the modes of variability, right? Yeah.
Stefan is also asking, this will be to filter out high frequency variability of the global coupled system. That again links to what you were saying earlier. I would like to take a question from Doug that is typed here. Thanks for a nice talk, Iuliia. Do you have any key recommendations of things to do or not to do for groups developing new decadal prediction systems for CMIP 7? This is a good question, Iuliia. Tell us what you think.
Yeah, what we have, but it's always a matter of resources. How much resources that the new group has, for instance. If they have limited resources, then probably they could go ahead with the nudging procedures, which is where you introduce this external reanalysis into your prediction system. But there are several kind of recommendations that I would check the variability of the external reanalysis, the variability of the model, and pick the reanalysis which are more common to variability of the model to avoid the problems that I showed you before in the presentation. If there is more resources, I would probably invest into assimilating the data directly into the model, just again to avoid these problems of introducing errors from another model, or just then having the fact to deal with this extraordinary variability which is coming from this external reanalysis. So at least this recommendations I can provide more. You can contact me also later.
Sure. There is also one more question I see. We can maybe take it for a couple of minutes more from Hugo Wang. Thanks for the great talk, Iuliia. How to better compare initialized and uninitialized predictions? The trend, because it is written as a comment, the trend will only remove the linear trend due to external forcings. Thank you.
Yeah, yeah, this is a good question. I'm also interested because when I see those comparisons with the historical simulations, it's also the one that I showed you in this presentation that can be really depressing at some point. So I'm interested in that method too. I can say that I know very good. I think that Doug Smith also has introduced the metric to better retrieve information from initialized predictions. Yeah, currently.
Yeah, we could continue this discussion for hours. Really, it's very. You touched many interesting points, and you know, I would like to ask you also many questions here. I don't know whether you would like to answer very quickly. One that you say that on one hand we have models that are imperfect, so we have these model biases that cause the drift, and on the other hand we have imperfect data sets. You know, we have discontinuity in time and as well in the distribution, spatial distribution of the data. Which of these two you think that actually introduces more serious consequences? So the problems that you are facing here come from both of these. In decadal predictions, more specifically, do you think that it's the problem is the models or the problem is the missing data more?
Yeah, that's a good question.
Because
I think that you can kind of downscale this to a very kind of rough kind of form. One of their colleagues from the project where I worked once said garbage in, garbage out. That could be probably answer in a very kind of simplistic way. If the data would be not good enough, then why would you expect that you would have a good prediction? Yeah, so I guess the quality of data and the amount of data is very important. Yeah, I think I can't choose between the two. I think both are really important. If the model is not able to simulate the processes realistically, then it would just give you the things that it can simulate, but it does not necessarily have something to do with the real world. Yeah, so I can't choose between data and model.
There are so many interesting. Yeah. There are interesting comments also appearing and questions, more questions. I don't know whether we can stay here for much longer. I wish we could continue this discussion, but we are at the 1 hour limit, and maybe you could take a look as well at the question and answers session. I can save this for us, and maybe you will come back to the persons who have more interesting questions raised. But I think we need to close this shortly.
Yeah, thank you very much. Thank you for all the questions. I will have a look and will try to respond.
In fact, there are many more interesting questions. So I just saw that they're appearing now. But thank you very much, Iuliia, for the nice talk.
Yeah, thank you for inviting.
And everyone for attending. Thank you very much, everyone.